So in last class we have seen what is stress actually and the different type of stresses. Now after studying of these stresses, this much clarity we should have. If I am asking a simple question, if I am posing a simple question, what is the stress, what is the maximum value of stress in a body? The simple question anyone can be asked, what is the maximum value of the stress in a body? The simple answer as per we have studied in the last class, it is if you are considering a uniform cross section, the stress will be same at every point. The simple answer given by the student. But because stress is the point description, so the value of stress will be maximum at a point where the load is actually acting. Just like this, if I am considering this, I hope the question is clear to everyone. If anyone is asked, suppose this is a body, this is an object, you can say, and the force is acting over the object, like P is acting over the cross section, and the cross section is nothing else, that is the A. Now the simple question is that what is, because it is the uniform cross section area, so the simple question can be asked, the point, what is the point at which the stress is maximum? So the student simply give the answer, the stress is uniform throughout, the maximum, and the value of maximum stress will be nothing else, that is the load by area. But it is not a correct answer, because stress is a point description. It is a point, stress and strain are the point wise description, not the body wise description, right? So the stress will be different at the different points, and where it will be maximum, and definitely the stress will be maximum at a point at which, or at a cross section at which the load is acting. If I ask the simple question, suppose any person is trying to pull me from this finger. If any person is trying to pull me from this finger, suppose any person is pulling this finger, the simple question is that which part of the body will feel more stress, or which part of the body will offer the more resistance? So you can think. So simply you can give the answer that definitely the part at which the force is applied, that will offer the more resistance. Means the finger itself will offer the more resistance. Then the next joint, then the next joint, then the next joint, then the next joint. So this way the value of stress or the value of resistance offered by the different parts of the body will be the different and going to be the uniform as we are going far from the application of the force. So practically we can simply understand, and that's why we are also describe that stress is a point wise description. Stress not depend upon the area wise description. It is not uniform throughout the area, but we assume that because we are considering infinitely small area, and we are idealizing that infinitely small area as a point. So there is a scientist, Sant Venant, they given a principle that is called Sant Venant principle. According to that principle, if we are considering any body and it is subjected a load like this, if any body is subjected to the load, right, the point that is nearly about B by 4, and what is B? B is nothing else, that is the maximum lateral dimension. Lateral dimension means if I am having a 3-dimensional body, so one is in the direction in which I am applying the force is called as the longitudinal direction, other 2 direction are the lateral. So I am considering B is the maximum lateral dimension, right? Anyone, it may be the width or thickness, whatever the maximum out of 2, I am considering that maximum dimension B. If I am moving a distance of B by 4, so it is simply observed that the variation of stress is like this. The stress is varying like this. Means at the center, where the force is applied, the maximum value of stress is nearly about at this point the value of stress is 2.58 times of 2.58 times of average stress. If we are moving far from this point, means if we are moving at a distance nearly about b by 2, this distance is b by 2. The variation of his stress is something like this, and it will reduces definitely at we are going far from the point of application. The peak is going to reduces, and at this point the value is 1.38 times of average value. We are moving further. If we are moving a distance that is b itself, it is b. The variation we will observe and surprised to see the variation. It will be very the value is very low at this point. Actually the peak is very low, almost we will able to see the uniform variation. Can you imagine? That is 1.03 times of average stress. If we are moving a distance, how much? 3b by 2. It is 3b by 2. We can simply observe the variation is uniform, means there is no effect of the force line of action. At this point the maximum stress is equal to the average stress. So according to the Sant Venant principle, the cross section, the point at which the force is acting, the body will offer the more resistance. When the body will offer the more resistance, the value of stress will be maximum. So answer of this simple question is that the stress will be maximum at a point or in a line which is near to the point of application of the load, right? So as we are moving far from the body, the stress is almost uniform at a distance of 3b by 2. So whenever we are writing the stress, we are taking an assumption, we are writing the average stress when the stress is uniformly distributed. So that's why whenever the question it is asked, so simply we always write the stress is nothing else, that is the load by area. When we are writing this stress, we are writing at a distance of 3b by 2. We are writing here, right? I hope it is clear. So whenever we are writing stress, we are writing the average stress. That's why we are also called the normal stress is equal to the average stress, and also called the shear stress is also known as the average shear stress, because whenever we are writing stress, we are writing when the stress is uniform, and the stress is uniform after moving a distance of 3b by 2 in a body. So stress we have seen. So there are two response of any force acting over a body. If any material, if the force is acting over the material, it has two response. One is stress, and stress can be experienced. It may be the normal or shear. Either the stress may be normal or shear, depend upon the external load acting over the body, right? Another response that can be measured, that is known as the strain. So now we will see the strain, how the strain will act on the body. So what is strain? If we simply define what is strain, so simply we can define strain. A body is said to be strained whenever the relative position of the particle if changed due to the load. So the standard definition or the general definition of the strain, any body is said to be strained whenever the relative position of the particle is going to be changed under the action of the load. Means if we are applying load over the body, there may be a possibility there is a change in position, relative position of the particle, and this change may be dimension change, and this change may be the shape change, means linear or angular, that depend upon the type of external load acting over the body. It is very important to understand, because student always confuse. Generally student define what is strain. The strain is change in dimension to the original dimension. That is the normal strain, because strain is depend upon the type of load acting over the body. If the load is normal, there is a possibility of dimension change. If the load is tangential over the body, there is a possibility of shape change, right? So the general definition of the strain you can define, a body is said to be strained whenever the relative position of the particle if changed due to the load, correct? Similar way we have defined the stress, we can define the strain, types of strain. So there are two types of strain again. Normal strain is represented by epsilon, shear strain is represented by gamma, correct? If the load is normally acting over the body, so there is a possibility change in dimension to the original dimension. So what is the normal strain? Normal strain is the ratio of change in dimension to the original dimension. Means when the load is acting normal to the body, normal load will cause the change in dimension, and that change to the original dimension is known as the normal strain. Now come to the shear strain. If the load is acting tangential to the surface or the shear load is acting over the body, what is the possibility? There is a possibility of angular deformation. If there is a possibility of angular deformation, so how we can define the shear strain? Angular deformation means change in shape. If a body is angularly deforming, what is the meaning of that? There is a change in shape. So shear strain is represented by gamma. That's why it is represented by an angular term gamma. And that is nothing else, that is the change in shape to the original shape. Change in shape to the original shape. Right? I hope it is clear to both. Normal strain and shear strain. Normal strain means change in dimension because load is normal, so there is a possibility, there is a change only in the dimension. If the load is tangential to the surface, there is a possibility, just like you can also visualize by considering this example. If I am considering any block and it is fixed at bottom face, if I apply a force over it here, so what will happen? Because bottom end is fixed and I am applying a tangential load, so there is a possibility of angular deformation. This angular deformation is nothing else, that is called as the shear strain. So there is a possibility of shape change. Because the load is tangential, there is a possibility of shape change. So that's why I am defining shear strain is nothing else, that is the change in shape to the original shape. In case of normal, what is the meaning of normal strain? Whenever we are applying load normal to the surface, what happened after the application of the normal, suppose the length is L, after the application of the force, the length will increase and diameter will decrease. So the final length become, suppose this is Li, this become Lf. So what happened actually? There is a change in dimension. If the load is normal, the strain produces normal strain. If the load is tangential, the strain produces shear strain. Normal strain is change in dimension. Shear strain is change in angular deformation, change in shape, angular deformation. That's why the shear strain is more dangerous, because the shape of the body is going to be changed, right? Further, we can define normal strain into three different parts. One is called longitudinal strain, lateral strain and volumetric strain. So the meaning of longitudinal strain is, if the load is acting along the length, or you can say any change taken place in the direction of the applied load to the original dimension of that direction is known as the longitudinal strain. Just like this, if I am considering a block, suppose I am considering this block, initially it is an object and the diameter, initial diameter of this object is di, and the length of this object is, we can consider is Li. If I am applying the normal load, because we are studying the normal strain, so we have to apply the normal load. So suppose I am applying a normal load like this along the axis, what will happen? Because the normal load is the type of load is tensile load. So tensile load has the tendency, what will happen? The length will increase and diameter will decrease. So after the application of the force, what is the possibility? The length will increase. Suppose the final length become LF and the final diameter become DF. Final, basically. So final, this become DF and this final become LF. I hope it is clear, right? Because the type of load is tensile, so the length is increases and the diameter is decreases. If the type of load is compressive, so vice versa, you can say, because the diameter will increase and length will decrease. Okay. So how we can define the longitudinal and lateral strain with the help of this example? So as I am describing that longitudinal strain is the ratio, or you can say, because it is the type of normal strain, and normal strain is nothing else, that is the change in dimension to the original dimension. Now the important factor is which dimension. Okay. In case of longitudinal, which dimension we have to consider? So the dimension we have to consider in the direction of the applied load. In the direction of the applied load, whatever the change is taken place to the original dimension of that direction. Just like I can write, because I am applying force in the x direction, so the longitudinal strain in x direction, what is the value of that longitudinal strain? The final length become LF and the initial length is Li, and what is the original length? That is Li. So we can simply write delta L over Li. That is called the longitudinal strain. This is nothing else, this is the longitudinal strain. So how the longitudinal strain is defined? It is defined as the change in the dimension in the direction of the applied load to the original dimension of that direction is known as the longitudinal strain, right? Lateral strain is whatever the change taken place perpendicular to the applied load, because we are applied load in the x direction. If I am considering these are the two direction x and y. If I am applying load in x direction, right? So the change in x direction is I am calling as a longitudinal strain. Change in perpendicular to the x direction, that is known as the lateral strain. How the lateral strain is defined? Whatever the change taken place perpendicular to the applied load, it is known as the lateral strain. Okay. So how we can define the lateral strain? That is in the y direction. What is the change? The final diameter become df and the initial diameter is di and the original dimension of this direction is di. So that is delta d over di. And what is the value of this? Negative. This is called the strain in y direction, and that is also the strain in z direction, right? Because in both direction we are considering if the body is three dimensional, that is the delta d over di, and these will be same if the material is homogeneous. If the material is homogeneous, so we can say whatever the change taken place in y direction will be the same as the change taken place in the z direction. So this is called the lateral strain. So it means we can conclude here longitudinal strain and lateral strain always in opposite nature, because if I apply the tensile force, the length will increase, diameter will decrease. If I apply the compressive force on the same object, so the diameter will increase and length will decrease. So always longitudinal and lateral strain always in opposite direction. Another conclusion is that every three-dimensional body has one longitudinal strain and two lateral strain. Every three-dimensional body associated with one longitudinal strain and two lateral strain. These are the conclusion from these strain. Volumetric strain is also the, you can say, the type of normal strain. As the word indicating, volumetric strain is nothing else, that is the change in volume to the original volume. Change in volume to the original volume. So the volumetric strain is nothing else, that is defined as change in volume to the original volume. change in volume to the original volume. Change in volume to the original volume, correct? So this way we can understand the types of normal strain, okay? So further we can see the example of these strains. So these are the definition written here. I have also described, right? With the example I have also described. This is called as the change in dimension, contraction in the dimension if the type of load is tensile, type of load is compressive. So this delta over initial length is L, that is called the strain, longitudinal strain, and here this delta by L, that will be the negative, that is also called the longitudinal strain. Here the lateral strain, that is the change in diameter delta D over D, right? This way we can define longitudinal and lateral strain, and this way we can define the change in volume. If the force is acting in all three directions, right? So whatever the change taken place, so the volumetric change is nothing else. You can write strain in x direction, strain in y direction, strain in z direction. If we add strain on three direction, we are able to calculate the volumetric strain simply, right? Or we can say, if we are considering any body that is a rectangular plate, suppose if we are considering any rectangular plate or any cubical body like this, so we can say what is the volume, LVH or LVT, anything we can say for the any rectangular plate. If I am considering any rectangular plate, what is the volume of that rectangular plate? LVH. If I do the partial differentiation both the side, so what is the partial differentiation? Just we have to differentiate with respect to variable, other variable become constant. So I can write like this, del V, or you can say del B is equal to del L, BH remain constant, plus L del VH plus LV del H. If I divide by the total volume is nothing else, that is LVH, LVH, LVH. So what will get? This del V over B is known as the volumetric strain, and this BH is VH, so it becomes delta L by L plus delta B by B plus delta H by H, and that becomes strain in x direction, that becomes strain in y direction, that becomes strain in z direction. That is the volumetric strain. So we can also calculate volumetric strain in this way, that is change in volume to the original volume, or we can also calculate strain in x direction, y direction, z direction, and able to calculate the volumetric strain. If the body is rectangular plate, this is the rectangular plate. If the body is cylindrical, so what is the volume of the cylindrical body? Pi by 4 d square L, right? So in that case, what is the volumetric strain? 2 times del d over d plus del over L. Simply we can partially differentiating both the side and divided by the total volume. If the body is cubical body, so the cubical body, the volume is 4 by 3 pi r cube. So what is the partial differentiation? Volumetric strain, that is 3 times del r by r, okay, because the change taken place in all the direction is the radius change, correct? So this way we can calculate the volumetric strain. Now the another question come into the mind, shear strain. How the shear strain is defined actually? So we have seen the example of normal strain, and normal strain may be longitudinal, lateral and volumetric. And how we can define the term shear strain? As I have discussed already, shear strain is nothing else change in shape to the original shape, because after the application of the tangential force over the body, there is a possibility of shape change, because that is in the terms of angular deformation, right? So this is the example of shear strain. If I am considering any cubical body and fix the bottom face, after the application of the top face of the tangential force, what will happen? There is a possibility of angular deformation, and this angular deformation is called phi, right? If write the tan phi here, so we can see what is the tan phi here. Tan phi is nothing else, suppose this is A, B, C D, and after the application of the force, that become D dash, that become C dash. Sorry for that, right? So if I am writing tan phi here, so what is the value of tan phi? That will be equal to, suppose this is x, that will be the x over AD. If phi is very small, so I can write tan phi is equal to phi. So the phi is equal to x upon AD, and this phi is nothing else, that is called shear angle, and shear angle is always equal to the shear strain. So here shear strain is x by AD, right? Also the shear strain is also defined as, it is defined as the change in initial right angle between two line element which are parallel to x and y axis respectively. How we can define the definition of shear strain? Shear strain is also defined as change in initial right angle. Suppose this is the initial right angle. How much is the change taken place in the initial right angle between two line element which are parallel to x and y axis? So this way we can also define the shear strain, and shear strain is always in terms of angular deformation, right? So the question again come to here. One question can simply ask, can we calculate this x theoretically? Is there any possibility we can calculate x theoretically? Or we can say we can calculate strain theoretically. So the answer of this question is simple, that we cannot calculate x theoretically. We have to conduct an experiment. Experimentally we have to conduct one experiment. We have to consider a material, we have to consider a body, then we have to apply the tangential force. After the application of the tangential force, we are able to observe how much angular deformation taken place in the body. So theoretically we are not able to calculate strain. We can only calculate strain experimentally by conducting an experiment. So if we are interested to calculate strain theoretically, what we have to do? That's why the elastic constant come into the picture. Elastic constants are used to develop the relation between stress and strain, or to calculate strain theoretically. Because we have seen here we cannot calculate x theoretically. If we are interested to calculate x, we have to conduct an experiment. Experimentally we can calculate strain. If we are interested to calculate strain theoretically, we have to use the material constant. So the elastic constant and the material constant are used to develop the relation between stress and strain, or to calculate strain theoretically. Because stress can be calculated theoretically. We know the external load, we know the area, so simply we are able to calculate stress. But strain can't be calculated theoretically, we have to conduct the experiment. If we are interested to calculate theoretically, we have to use the elastic constant. So our next topic is elastic constant, okay? So for any homogeneous and isotropic material, there are 4 elastic constant. So the significance of the elastic constant we have seen, because strain is not calculated theoretically. So we have to develop the relation between stress and strain, or to calculate strain theoretically, we are using these elastic constant. For any homogeneous and isotropic material, there are 4 elastic constant. The word homogeneous and isotropic. Homogeneous means if the elastic constant are same at all the point. They may be different in the direction, but point wise they may be same. Means if there is any body, if I am considering this point, the constant is E here, E1 is here, E2 is here. They may be different in the direction. If I am considering another point on the body, the same elastic constant must be there. Right? Any material is said to be homogeneous material if all the elastic constant are same at each point on the body. They may be differ in the direction, because you can see here E, E1, E2, they may be differing, they are different in the direction. But if I am considering another point on the body, they may be similar. Just like wood, aluminium, composite material, some of the composite materials are the example of homogeneous material, right? Isotropic. The meaning of isotropic means material constant are same in all the direction. Suppose if this is even, means all constant, elastic constant or material constant same in all the direction. They may be different. Suppose if I am considering another point, so the value may be E2, but in each direction they may be same. Just like these are also the example of wood, brass and different composite and alloy we can consider under these, right? So any material which has both the property homogeneous and isotropic means material constant are same at point as well as same in direction. That is called as homogeneous and isotropic materials, right? Which are having the both properties, same in all the directions, same in all the point. So there are 4 elastic constant for that purpose. One is elastic material, that is called modulus of elasticity, also known as Young modulus. It is also known as Young modulus. Another one is modulus of rigidity. In some books, it is also represented by C. Bulk modulus, it is represented by K. And fourth one is the Poisson's ratio. It is represented by mu. So these are the 4 elastic constant we have to understand. Okay, and for which purpose these elastic constant are used? These are used to develop the relation between stress and strain and to calculate strain theoretically. And which elastic constant are responsible to calculate which strain theoretically, we will see in the next class. Thank you.